Hi, welcome back to lecture. This time we're going to go through section 9.2. We have done 9.1. 9.1 was difference of two means where the data was independent. And then we looked at 9.3, and that was the difference of two means where there were paired data. So there was some coupling. It was either the same person before and after, some medication, some magic shoes. 9.2, we're going to look at proportions. So we're going to look at a proportion of one group of people, proportion of a second group of people. We're going to assume that they're independent, they're not the same group, and then we're going to look and see if there's any difference between those proportions. So let's get started. I'm going to get rid of me. So here's kind of a question that we would be looking at. Here's a difference between two population proportions type question. The General Social Survey took a poll that asked 350 employed people aged 25 to 40 whether they used a computer at work. 259 of those said they did. They also asked the same question of 500 employed people aged 41 to 65, and 384 of them said that they used a computer at work. So if we calculate the proportions between each one of those two groups, we're going to assume the first one was the age 25 to 40, 259 out of the 350, if we do that proportion, we get a decimal point 740, or 74% of those did use computer at work at that age group. For the age group 41 to 65, those proportions were 384 out of the 500 polled. That was 0.768 as a ratio, and then 76.8%. So what we're going to ask then, is there really a difference there? 74% and 76.8%. Is there really big enough difference that we can say there's a difference in those age groups that use computers? Is there a difference in the proportions? Or is one bigger, or is it close enough? Okay. So the sample proportion is larger among older workers. The question of interest, however, involves the population proportions. Those are just the samples. Remember, if we continue to do different samples, we would expect different values, but they would be tightly coupled. They would be, pretty close. There are two populations involved. The population is of all employed people aged 25 to 40, and the population of all employed people aged 41 to 65. The question that we're concerned with is whether the population proportion of people aged 41 to 65 who use a computer at work is greater than the population proportion among those aged 25 to 40. So this is an example of a situation where we have two independent samples involving sample proportions, two different age groups, and we're asking somewhat the same question. So here's the notations we're going to use throughout this section. P1 and P2 are the population proportions of the category of interest in the two populations. So P1 is a population proportion, P2 is the population proportion for that. P1 hat and P2 hat are the proportions in the two samples. So P1 hat would be our aged for the first one, and then P2 hat would be the proportion for that second sample. Now the X1 and X2 we'll refer to, those are the numbers of individuals in the category of interest in the two samples. So if we go backwards, that would be, the X1 would be 259, N1 would be 350, X2 would be 384, and then N2 would be 500. And that would make up the P1 hat and the P2 hat once we did the calculations. So here is kind of the things that we're going to work toward. The issue is whether the population proportion of older people who use a computer at work is greater than the population proportion of younger workers. We being with the null hypothesis, which states that P1 is equal to P2. Now again, different ways we could look at this, that we could also say that P1 is less than or equal to P2, or P1 is greater than or equal to P2. But then we would have to look at the different alternate hypotheses. And if we just consider just the P1 equal to P2, it's a possibility that we have P1 less than P2, P1 greater than P2 or H1 P1 not equal to P2. So this is kind of it's either this or that when we're talking about that one. So the test statistic is based on the difference between the sample proportions P1 hat minus P2 hat. We're going to assume that there is no difference. So we're going to assume that P1 minus P2 is equal to 0. They're the same, so the difference would be 0. And then we're going to look at them for the difference ones as we go. When the sample sizes are large, this difference is approximately normally distributed, so the test will be based on the normal distribution. And here's what we're talking about if we had all the data and we could deal directly with the proportions. We would just say the mean difference is the difference between P1 minus P2. And the standard deviation of these would be P1, 1 minus P1 plus P2, 1 minus P2, N1, and here's the N2 in the population. We don't know what P1 and P2 is, note, and we wouldn't know what N1 probably and N2 is as well. But if we knew everything, that could be the mean and the standard deviation, and we could work things from there. So we don't know what P1 and P2 is, so we're going to use an estimate for hypothesis testing. This is only for hypothesis testing. We'll do a little different when we do confidence intervals. So to compute the test statistic, we must find the values for the mean and standard deviation of the sampling distribution. The mean is straightforward. Under the assumption that H0 is true, these are the same, so the difference would be equal to 0. The standard deviation is a bit more involved. It depends on if we knew what P1 and P2 were. We don't know what that population proportion was. So we're going to do this. We're going to calculate some P hat. Notice it's not a P1 hat or a P2 hat, but it's a pooled proportion. So this P hat kind of averages out everything somewhat. We do X1 plus X2 divided by N1 plus N2, and that's the pooled proportion. And it turns out that the standard error, remember sampling distribution, standard error is P hat 1 minus P hat over N1 plus P hat 1 minus P hat over N2. And this simplifies down to P hat times 1 minus P hat. Looks like P hat Q hat, 1 over N1 plus 1 over N2. So this is a pooled proportion. We're assuming that P1 and P2 are equal, and then we're going to calculate that based on there. So that's the standard error. So here's the test statistic. Once we go through and we're going to calculate that for the p-value, we're basically going to use the test statistic, or for critical regions, where does this z-score fall? Z, anytime I use z, I'm talking about the normal distributions. And the z-score is P1 hat minus P2 hat. Those are the individual sample proportions, and then the pool proportions for our standard error. And notice that over here, there's nothing over here, but this is minus 0, which was the P1 minus P2. So here's our assumptions that we're going to go through with proportions. We have 2 independent simple random samples. Each population is at least 20 times as large as the sample drawn from it. The individuals in each sample are divided into 2 categories, and both samples contain at least 10 individuals in each category. So basically that was saying that there was no overlap between the 2 proportions. And then this is our general hypothesis testing method. We do our claim, so this is kind of in there. We do a claim, a complement. We have to have those 2 values. Then from there, the equal is the null and alternate hypothesis. If we're going to make a decision directly, we need to do a significance level alpha. We compute the test statistic. We could also do the p-value based on that test statistic and then leave it for later to determine what alpha we need to do. The p-value won't change based on the alpha, but it would do for if we did critical regions. And when we do the final p-value comparison to alpha. So once we've got all of this set up, we go to the alternate hypothesis, and that lets us know which one we are, left-tailed, right-tailed, two-tailed. based on the null and alternate hypothesis. And then once we've calculated the probability of a probability greater than this value, that's the p-value. If making a decision, we reject H0 if the p-value is less than or equal to the significance level alpha. And then we state our conclusion. So now that we've got the procedure down, this is similar to all the other procedures that we've done for hypothesis testing. We just need to go through the calculations. So here we have our two groups. The General Social Survey took a poll that asked 350 employed people aged 25 to 40 whether they used a computer at work. 259 said they did. They also asked the same question of 500 employed people aged 41 to 65. 384 of them said that they used a computer at work. Can you conclude that the proportion who use a computer at work is greater among those 41 to 65 than among those aged 25 to 40? So we would want to know if P1 is less than P2. So we first check the assumptions. We have two independent random samples. The populations are more than 20 times as large as the samples. The individuals in each sample are divided into two categories with more than 10 individuals in each category. So the assumptions are satisfied. So now we just need to go through and do all of our calculations. Here's our pool proportion, x1 plus x2 over n1 plus n2. That gives us a pooled proportion right there, the 259, the 384, 350 plus 500 is the n1 plus n2. So that gives us a p-hat of 0.756471. The test statistic is based on our P1 hat sample, our P2 hat sample, and then there again is based on our pooled proportion. There's the 7.5, so the P1 hat was 0.740, P2 hat 0.768, gives us a negative value, and then there's our pooled P hat, 1 minus P hat, 1 over N1 plus 1 over N2. And if we're careful, we'll come out a z-score of negative 0.94. And if we did, here's our picture, and it's always good to draw a picture to see what we're doing. So if I had critical values, I'd also plot my critical values in here, left-tailed, right-tailed. So here is what we were doing. We were saying P1 is equal to P2 versus P1 less than P2 or P2 greater. This is toward the left for the P1. So it's a left-tailed test. I want to know the probability in here. So I'd go to the table, standard normal. Give me the probability to the left of a z-score of negative 0.94. That probability is directly 0.1736. One tail is just that probability value, and that's then called the p-value. So that 0.1736 is bigger than 0.05 that we were doing their alpha level. So we do not reject H0. We cannot reject the possibility that P1 is equal to P2. So if I can't reject this one, there's insufficient evidence to support our claim or what we really wanted to show, that P2 was greater than P1. So we cannot conclude that the proportion of workers aged 41 to 65 who use a computer at work is greater than the proportion among those aged 25 to 40. And we always say at what level we've done this thing at, and that's at the alpha 0.05 level. So for those of you who are lucky enough to have the 84, there is a two proportion z-test that you would go through. You would enter, you would say, here's my x1, 259, n1 over 350. So those are those enters. 384, 500. We are going to be P1. So we're assuming P1 is equal to P2. What is the alternate? Is it not equal, less than, or greater than? This is the one that we did, where our P2 population was greater than our P1 population. And then once we calculate it, here was our p-value, our z-score, everything comes out. Here's our P1 hat value, our P2 hat value, our pooled value, the p-hat, N1 and N2, that gives us everything. So this is the output that you would see if you had a TI-84 Plus calculator, and at sometimes on the test we may give you this output. Here's the input and the output, and then ask you to make decisions based on that. Notice that this is P1 less than P2 because of here. That tells you what you were testing against. Mini tab, the difference. Here's sample 1, sample 2, sample proportions. Sample 1, sample 2. The difference of P1 minus P2, the estimate for the difference is negative 0.028. And then the 95% upper bound for the difference is 0.021556. Test for the difference, equal to 0 versus less than 0. So this would be P1 minus 2, P2. So this is interpreted as P1 minus P2 less than 0. So that's why versus less than 0. Z-score for my calculation, the same thing. And then there's our p-value that we would directly go and draw our conclusions from. So let's say if we did the very same thing and we're just going to do the critical value. I just need the Z alpha, which has an area alpha to its left. So if I'm left-tailed, I get the full alpha. Right-tailed, I get the full alpha. And then the two-tailed, I need to split the alpha on the outside. And remember what alpha is. It's just 1 minus the confidence, like if you had the confidence on the inside. So out of a total of 82,486 accidents involving drivers aged 15 to 24 years, 4,243 of them, or 5.1%, occurred in a driveway. Out of a total of 219,170 accidents involved drivers aged 25 to 64 years. 10,701 of them, or 4.9%, occurred in a driveway. Can you conclude that accidents involving drivers aged 15 to 24, our first group, are more likely to occur in driveways than accidents involving drivers aged 25 to 64? So you're asking if this proportion is greater than this proportion. This is going to be our P1. This is going to be our P2. So as P1, can we conclude that P1 is greater than P2? So let's go through and set everything up. 2 independent samples. Individuals in each sample fall into 2 categories. Those are those 2 age groups that we're working with. And then the null and the alternate hypothesis we're stating, is it going to be actually less than or equal to, but this is kind of the simplified version. It's just P1 is equal to P2 versus P1 greater than P2. Okay. Can you conclude that accidents involving this drivers are more likely, so more of a percentage from P1 than P2? What does that make P1 minus P2? P1 minus P2 greater than 0 in this case. So here's our pool proportion. Let's go through with this. Here's our X1 plus our X2, N1 plus N2. So that gives us our standard error. P1 hat minus P2 hat, they gave this directly when we went through as a percentages. We can just do those as proportions, not as percentages. Which version? A right tail test, because it's pointing to the right. The P1 is always to the left side, and then relationship to P2. So it's greater than P2, so that's pointing to the right. Now we had at the alpha 0.05 level, I go through and I look, standard normal because I'm talking about Z's, area to the left, full area to the right on that right tail test, the right tail test would be 0.05, 0.95 is here, so the inverse is 1.645. Find the Z-score, whose area to the left corresponds to 0.94, that's the inverse, and that's the 1.645. That sets up between our critical region, rejection region in the tail, fail to reject in the main part, and then here's our Z-score, 2.95. This would be, the hump would be 0, 1.645 at critical, 2.95 is in the tail further in that critical region, in the rejection region. So we reject, what do we reject? H0, this possibility right here. So we're also rejecting the possibility that it could be less than or equal to P1 less than or equal to P2. Any of those, this would be the greater one, and we would reject. So since we clearly reject this one, we have enough evidence to support this. So at the alpha equal to 0.05 level, there is sufficient evidence to conclude that the proportion of drivers in that age group in a driveway is greater than the proportion of the P2 group. That's the 15 to 24 P1 group, and my P2 group is the 25 to 64. So now let's move on to confidence intervals. Confidence intervals we're going to do a little differently. We don't know what, so when we do confidence intervals, we don't build them for P1 equal to P2 and then say, well, the pool difference is a good measure standard, the standard error. So consider the following example. In a study of the effect of air pollution on lung function, a random sample of 50 children living in a community with a high level of ozone pollution had their lung capacities measured. 14 of them had capacities that were below normal for their size. A second random sample of 80 children was drawn from a community with a low level of ozone pollution, and 12 of them had lung capacities that were below normal for their size. We are interested in studying the difference between the proportions of individuals in two different categories. One from a group of that had ozone pollution, one for a low level of ozone pollution, and then look at the difference of the lung capacities. So here's our notation again for this one. P1 and P2, those are always the population proportions of the category of interest in the two populations. The proportion that had lung capacities that were below normal and high level of ozone pollution, P2s were a low level of ozone pollution. X1 and X2 are the numbers of individuals in the category of interest in the two samples. These are the only things that we can deal with and then kind of estimate the difference between the two population proportions. N1, N2 are the two sample sizes. So now we're going to do this. Now, I'm just going to shoot down here real quick. Look at the standard error. Here, in hypothesis testing, we dealt with just P hat. That was the pool proportion. Here is the proportion from the sample from group 1, proportion, and the sample group 2. So the point estimate, we always start when we're talking about confidence intervals. We need a point estimate in the middle, and then we have some margin of error on both sides. Here's what we're concerned about. We want to know some estimate of the difference between the two population proportions. Our point estimate, our first estimate that we're going to deal with, is just those samples that we got, the P1 hat minus the P2 hat. So here's the variances. Basically, it lets us know here's from the population. We need to know the variance of the difference between these two. And this is the best estimate of this, is the variance of P1 hat minus P2 hat is this guy, and that standard error would be that. P1 hat minus Q hat, P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N2, take the square root. So that was the standard error. The margin of error is always the standard error times the T alpha over 2 or Z alpha over 2, whatever distribution that's going to give us the margin of error. And in this case, it matches. We're still going to do the normal distribution, Z-scores. Where's our alpha from? That's based on the confidence level 1. My alpha is going to be 1 minus C, the corresponding. So these are very similar. Our assumptions are very similar to our hypothesis testing that we've covered just a few minutes ago. 2 independent simple random samples. Each population is at least 20 times as large as the sample drawn from it. The individuals in each samples are divided into 2 categories. Both samples contain at least 10 individuals in each category. So here we're going to go back to this with our ozone pollution. Naturally, this kind of meets all the criteria. So we're going to get started. Construct a 95% confidence interval for the difference between the proportion of children with diminished lung capacity between the 2 communities. So everything was there, so let's go through and set up everything. So our first group, our P1, is the first one that I come through and I read. This is kind of the general the way that you're going to do. 50 and 14, that's the P1, into P2, or X2, sorry. The N1, X1, into X2, and then that'll give us that setup. So the difference is always the P1 comes first, whatever that we're talking about first. Here's the point estimate, P1 hat minus P2 hat, 14 over 50 minus 12 over 80. That's 0.13. That's our point estimate. And then we've got to construct that margin of error. The critical value for a 95% confidence interval. 95, I start with this. So here, for this confidence interval, I'm always considering, I draw. I said, what confidence interval do I start with? 95%. So outside, this is the confidence interval. Outside is the alpha, which is 1 minus 0.94. Everything up under that curve is 1, so outside is the one that's the 0.05. But now I'm talking about 2 tails, and I split that between the 2. Alpha over 2, alpha over 2, which is half of this. If I divide that by 2, I get that 0.025. So here, 0.025. I go to my table, I go to the calculator, inverse normal through Excel, and I'm going to find what's that Z, what is this critical value, what is this value with 0.025 probability to the left, and that's what I should get. For this one, it's going to be like minus 1.96. It's symmetric. Plus 1.96. If I go to this one, I just drop the negative. So both of these are the 1.96. My standard error, again, here's the 0.28, 0.15, 0.28, 1 minus 0.28 over the N150. There's my N150. 0.150, that's the 12 over 80, 1 minus 0.150. Over the N2, and then I take the square root, I get that. So my next is my margin of error, and I just take that 1.96 and then multiply it times the standard error, which is the 1.96 times 0.0750005. So that margin of error is just the 0.14701. Then I just do my calculation. I start out with my point estimate. I add the margin of error, 0.14701, that gives me a plus, and then 0.130 minus 0.14701 gives me the negative. So here, this is clearly, this estimate in here includes 0. So if I wrote it as my interval, 0.277, I know this is all the numbers between negatives and positive, and 0 is right there in the middle or somewhere in there. Okay, So 0 says no difference. If that 0 was in there, this would be P1 minus P2 equal to 0, or P1 is equal to P2. Okay. So this is all we can say, is that it's between negative 0.117 and 0.277. This confidence interval contains 0. Therefore, we cannot be sure that the proportions of children with diminished lung capacity differ between the two communities. P1 may be less than P2. P1 may be greater than P2 once we get past there. And it also could be P1 is equal to P2. So based on this confidence interval, there's not a lot we can say about those. So we can do, with the TI-84, the two proportion Z interval command, X1, N1, I enter, and X2, N2, the C level, confidence level 0.95, and then when I do the calculate, it gives me the negative 0.017 to 0.27701. There's my P1 hat, my P2 hat based on those calculations, and N1 and N2. Other outputs, the Minitab output, which is a popular statistics package. It gives you a little test and confidence interval for two proportions. The difference, P1 minus P2, estimate for the difference was the 0.13. If we went back to here, there's the 0.13. It's the same thing. So it gives us, here's the estimate, is the P1 hat minus P2 hat. There's our 95% confidence interval. Test for difference equal to 0 versus not equal to 0. Z is equal to 1.73, and again, the p-value for this would be 0.083. 0.083 is bigger than the 0.05. And again, for this one, if you did this one, this was a two-tail test, so it's actually going to be twice that one that we actually gained. P-values when we're doing two tails is always twice that probability value. So 0.083 is bigger than 0.05. We fail to reject H0 in this case. Okay. So take a look at those, go through the textbook, get used to both the hypothesis testing, confidence intervals, and I'll see you next time.